Another topic that always confused me during my data science journey was about this linear transformation and matrices. Though I understood it, I never actually got to know that what is the actual meaning of this whole point. So today I'm trying to explain this whole concept to you in a better and more linear way. So actually, linear transformation. Till now, you might have seen the definition or like this. Linear transformation is nothing but a function or any type of transformation applied to a vector space, which transforms a vector v1 into another vector v2, right? So where this function is the linear transformation, and v1 belongs to one vector space and v2 to other. So actually, this definition is quite useful, but actually doesn't explain what the transformation is and how is it happening and what are all the different type of bits of all this uh, concept. So actually what does this mean linear transformation is that it is, imagine you are in the vector space of two-dimensional space. In the last video I explained that collection of all the 2D vectors constitute the two dimensions vector space, right? So imagine if you have this two-dimensional vector space. Now this space is made up of what? Grid lines, just like on a graph paper, right? Where each point is a coordinate, and to that point if we draw a vector we can show it like this. A belongs to A and B belongs to the real number set since they are part of the vector space R2, right? Now, any type of, imagine you have a vector V1 here in this two-dimensional vector space, just like a matchstick, fancy name for a list of numbers, vector. No. If we do any type of linear transformation on this, what does this actually mean? It means that imagine this whole grid, whole two-dimensional space is your graph paper. And if you do any type of linear transformation LT, which is a function of f, for example, it will elongate the paper, stretch the paper, fold the paper in any way, like this, or it might be like this. So this folding of space, it is just like the fold in a space-time curvature, but I'm not going into that scientific science fiction. The folding of the space is known as linear transformation. And due to this, what happens? The vectors inside it also get compressed or elongated, right? Imagine you are you drew a line, right? Now with the extension of this space, this line will also be elongated and most probably disoriented from its original direction, right? So this whole concept practically is called linear transformation. So you put a vector v1, and after the linear transformation you get a new disoriented vector v2. And how did you get it? By putting it into a function. And this function was what? The folding, and which we formally call in mathematics or linear algebra terms the linear transformation. This is the practical meaning of linear transformation, the folding of the space in which the vector is present. Folding of the vector space in which the vector v1 is present. Now, this, how does this folding occur? We cannot randomly fold in any direction, any orientation, right? So I will try to explain this. I think I should about this part. Now, this is the linear transformation. How does now you remember about the basis vector, right? We talked about this in the last video. So what is the basis? What are basis vectors? They are linearly independent vectors where one vector cannot be represented in the form of other vectors, right? Whose span, another fancy term for linear combination. Linearly independent vectors whose linear combination, that is span, they span the whole vector space, whole given vector space. So imagine if I give you two vectors I and j, which is 1 comma 0 and 0 comma 1. Their linear combination will span the whole vector space. alpha 1 1 0 and alpha 2 0 1. It will give what? Alpha 1 alpha 2 by vector addition, rule of vector space, right? Another vector of the same vector space. So these are the basis vectors. So you notice this vector space is comprised of these linearly independent basis vectors, right? This is the originating point of this whole vector space. These are like the parents of the whole vector space. So if we want to do any type of changes here, where we have to do the changes? In the basis vectors. So tell me, if you are doing a linear transformation of this whole vector space, just changing the vector orientation, where do we have to start? Yes, in the basis vectors. So this is the importance of the basis vectors. And when we do any type of linear transformation, this is the BV, the basis vectors is what is changed. So in a nutshell, any type of linear transformation when you are doing given two-dimensional space, very normal, very naive, is converted to an elongated space like this by a linear transformation. F of v1 is equals to v2, where f is the function that converts this into this whole two-dimensional vector space. This is happening due to change of basis vectors. Now, what is the type of change here? Initially, the basis vectors were I and j in vector form 1, comma 0 and 0, comma 1, right? These were the initial basis vectors. After the linear transformation, both are the same thing. Linear transformation of f of v1 equals to v2. The basis vector moved to a new position. Now, because you use these two vectors initially for those whole vector space, for this you might be using these vectors, basis vectors, right? So this is how these basis vectors were shifted to this new position. And this is how the linear transformation of the two-dimensional space and all the vectors inside it happened. Now, this is where the role of matrices come. Just remember this point. Basis vectors were moved to a new position led to the linear transformation, right? Remember this point. I should write it. Move to a new position. Let the new position be 2, comma 0 and 0, comma 2. So this is the new I of the new vector space. And this is a new J, right? Yeah, this is the new vector space after the linear transformation. Now, this is where the role of the matrices come. Matrices is nothing but just a storage quantity to store the new position of the basis vectors. After linear transformation, to store the new position of basis vectors or BV, we use matrices. So when you get a 2 cross 2 matrix, now what is the new position of these basis vectors? 2, comma 0 and 0, comma 2. And I will write it in the form of a matrix like this. So this is all about all the that humongous terms that you couldn't understand. That what is the matrices, what is the actual use of it, or what does it store? It's actually all crushes down to this. It stores the new position of the basis vectors, nothing else. Now let me. I will prove it also. I'll also prove it to you in a better way. This is our new position of I and j, right? So if this is a new position of I and j, and this is our matrix M, so if I multiply it with any vector v1, it will give me a new vector v2, right? This is the same thing what we are doing here. So linear transformation is nothing but same as multiplying the vector space. And when I say vector space, it means any vector of that vector space. So maybe multiply the vector space, that is any vector of the vector space, with a matrix M, which contains the new basis vector positions. It will give a linear transformation corresponding to it. So this is the actual meaning of linear transformation. F of v1 equals to v2 is same as m in dot v1 into v2. N dot v1 equals to v2. And this m is the new position of the basis vectors. I will also prove it to you. What was our I? 0, comma 1. Sorry, 1, comma 0, right? On the x-axis initially, before the linear transformation. If I multiply it with 2, 0, and 0, 2 matrix, what it should it give me? The new position of the by this theory, what is the new position of I? 2, 0. So it should me give me 2, 0. Let's see. It's a 2 cross 2 matrix, 2 cross 1, first row, first column, 2, second row, first column, 0. What was 0? So this means that my theory was correct. The I initial basis vector on the x-axis moved to a new position 2, comma 0, which is the new basis vector also. Similarly, if in any vector of the two-dimensional space, let us take 1, comma 2. If in the new vector space, where it will lie, I have to find it by multiplying it with the linear transformation matrix. 2, 0, 0, 2. First row, first column, which will be 2. Second row, first column, which will be 4. So 2, comma 4 will be the new position of 1, comma 2. This is the new in the new vector space corresponding to 1, comma 2 old vector. This will be the new vector, and this is how the linear transformation changes all the vector in that vector space. So in a nutshell, f of v1 equals to v2, which is a linear transformation, is nothing but m of v1 into v2, where m is a matrix containing the new position of basis vector, which is doing the linear transformation. That's it, the whole summary. I know it sounds a bit confusing, but if you watch this video 1 or 2 times, I think you will get it. It's all about perception. Unless and until you are able to visualize this, you cannot solve any questions or any type of theory or concepts in math. So this is all. Actually, there's one small concept also which I'd like to cover here. That what is the actual meaning of the determinant of a matrix? Just a small concept. So, no, when you say the determinant of a matrix is what for? What does this actually mean? It means in the two-dimensional space, the linear transformation done by this matrix, the new position of the basis vectors 2, 0, and 0, 2, the change done by this matrix. The determinant value will show the scale by which the unit area changes. The unit area changes after linear transformation, because if old vector space was this, and we draw a square of unit 1, after the linear transformation, the space might get squished down, and the area of the square also changes. And this area comes from the determinant value of the matrix M, which is doing the linear transformation here. MV1 equals to V2. So this is the actual meaning of the determinant of a matrix. Hope I was able to cover it.